Uh, First, I'd like to thank the organizer for this workshop. Liang has given some theoretical background of part of the experiment that I'm going to show you today. So I'm going to tell you about emergent quantum phenomena in crystalline graphene. Okay, no twist. Before I get started, I'd like to acknowledge all the people who contribute to the works I'm going to show you. These are my group at MIT, especially Zheng Guang used to be a postdoc in my group. Now he's a faculty at the Florida State University, and he is in the audience. So if you have technical questions, he's there to answer. We enjoy the benefit of collaborating with Ray Ashury's group on experiment at MIT and getting their support from Liang Fu's group, Fan Zhang, and some of the early data was taken in Hong Kong Park Steel Bridge. And we'll also get a nice HBM crystal from Japan. So I want to start from a general point of view, talking about emergent quantum phenomena. There are two famous examples that we're all familiar with. One is superconductors, where electron correlation effect, you get super pairs, perfect quantized zero resistance. And in another case, as Liang was telling you, that topological phases of matter usually measured by some quantized Hall resistance is another class of material, phenomena that emerge from the interaction and the topological protection of the interacting electrons. So through this many years of condensed matter research, we sort of know where to find such kind of phenomena. On one hand, in order to promote the electron correlation effect, you want to have some flat band, right, where the kinetic energy of electron is quenched, so the correlation or the interaction energy becomes more important and could completely change the ground state. On the other hand, if you want to look for topological effect, one common ingredient is you find some material that has big barrier curvatures. And that will give you anomalous velocity, and that can be integrated into quantize the Chern number. That's what you measure in the Hall effect, right? So these are some very general laws. Experimentally, you should ask like where to find them. Through decades of efforts in condensed matter, we know crystals where to look for them. For example, cuprates, you throw all these atoms into furnace, and the chemistry just magically give you something, shows high temperature superconductivity. Or you go one step further, you grow this vertical heterostructures and at the interface of these semiconductors, you get high mobility two-dimensional electron gas. And applying magnetic field completely quench the kinetic energy, give you a lambda level integer and fractional quantum Hall effect. So these approaches are based on atomic crystals. That's very successful. Well, in recent years, there is another opportunity that has been explored heavily by people in the two-dimensional material community, and we really see the advantage of engineering more flexible structures. Right, you start with this two-dimensional sheets, and there's no chemical bonding between layers to limit what kind of configuration you can have, right? So you can choose whatever two-dimensional materials and how many layers of them, and you can choose how to put them together by giving twisted angles. Well, you're still at the two-dimensional limit, which means you can still enjoy the in-situ tuning by tuning up something called electric field or gate electric field to change the charge density and the band structure of the material. Okay, especially in recent years, people realize that, as Liang told you, that you can introduce Moiré superlattice between two adjacent layers of 2D materials, and that can be done in two ways, right? So if you have two materials, for example, graphene and hexagonal boron nitride, which is a very nice insulator, they have a natural lattice mismatch about 2%, which means you can just put on top of each other without twisting purposely. If they're at just 0 degree, there will be a spatial heating of these atomic patterns, and that gives you a periodical Moiré potential. And of course, if you start with two materials that are exactly the same, for example, graphene, MOT2, and MOT2, you don't have that lattice mismatch to use, but you can still give it a twist. And that twist angle will also generate a spatially modulating Moiré potential. And that gives you an additional knob to control the kinetic energy as well as how electrons are talking to each other in this Moiré superlattice. So I was enlightened by both these two types of wisdoms, right? The older wisdom is chemistry is great, right? Crystal is great. It's very robust. It's very repeatable. However, it is really hard to tune because once the crystal is grown, there's nothing like gate electric field you can tune the property of the whole bulk crystal. While two-dimensional stacks, especially with Moiré, is very rich in the structure. And you can make use of the interactions. You can engineer how they interact with each other between layers to get new phenomena. However, you're suffering from a new type of disorder that you do not have in crystal, which is the inhomogeneity induced by the fluctuation of the Moiré superlattice wavelengths. For example, this is a work to use a scanning nanosquid to image twisted bilayer graphene. And because you may have heard there's a so-called magic angle between graphene and graphene that gives you superconductivity. But the thing is that magic angle is very precise. If you deviate a little bit from that angle due to some strain in your structure, you're going to lose the magic. So when you get superconductivity, you don't get a homogeneous superconductor where the supercurrent flow everywhere. You actually have a percolating network of superconductors that only pass through where you precisely hit that magic angle. Well, this is a new type of inhomogeneity that you don't have in crystal systems. So why don't we think about ways to combine these two wisdoms and take advantage of both of them and avoid the disadvantage, right? So what I'm going to do is to start with a crystal, but in the two-dimensional limits, okay? Two-dimensional crystal that already has flat band and, barrier curvature in it. And then I'm going to proximatize it by Moiré superlattice effect or some other things at the proximity of this two-dimensional flat band crystal. And hopefully, I can take advantage of the otherness of crystal, and I can also enjoy the benefit of proximity effect and the gate tuning. And that, hopefully give me electron correlation topology, okay? So the starting point is I need to find some two-dimensional crystal that already give me flat band and big barrier curvature. And guess what that material is? It's graphene, okay? Well, 2 decades after the discovery of monomer graphene in lab, what do I mean by flat band in graphene? Graphene has the largest permeability linear band, has nothing to do with flat band at all, right? Well, it turns out you can go beyond the monolayer, okay? And you don't have to twist. You just look at the exfoliated flake, and you've got different optical contrasts on the visible light. And that optical contrast simply tells you how many layers of carbon you have in the flake, okay? And it turns out the structure of graphene in the crystal form is more rich than just having different layer numbers. Because there's no chemical bonding between the layers, you actually can shift them to get different stacking orders, right? These are the 2 leading stacking orders you will find in every exfoliated flake of multilayer graphene. So there's no ambiguity in the case of monolayer or bilayer. Bilayer is always in the so-called AB stacking. Well, when you get to the 3rd layer, you have to choose whether to shift it to the left or shift it to the right. And that will give you the Bernal stacking, or known as ABA stacking, or the Rhombohedral stacking, which is known as ABC stacking. Okay, and this can keep going forever. Like if it's Bernal, it can go as AB, 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 AB. Well, Rhombohedral stacking can go as ABC, ABC, ABC. Of course, as you go thicker, there are even more intermediate stacking orders. So structurally, Bernal stacking is the most stable form of graphite. 80% of graphite is in Bernal stacking. Rhombohedral is a metastable form, but you can still have something like 10% chance of getting the carbons in the Rhombohedral stacking order. Well, it turns out from the point of view of correlation, flat band, and barrier curvature, Rhombohedral is much more interesting for the following reason. Okay. Oh, before I tell you about the reasons, let me show you, like, you can really see it. What do I mean by you can see it? Okay, so this is an optical image on the visible light. You see this is a big region that has the contrast corresponds to 4 layers of carbon, petrol layer. Well, that's it, right? Apart from a couple of dirts, you don't see anything else. However, if you increase the wavelength of the light you're using, so the light is more sensitive to the low energy band structure that may be different for different stacking order, immediately you see this optical contrast between different areas, and that contrast tells you what stacking order you're looking at. For example, this area here is corresponding to ABAB or the Bernal stacking. Well, here is ABCA corresponding to the Rhombohedral stacking order. And in this case, there's something else that shows you the so-called ABCD stacking order here. So you can really see it. Okay. And why is rhombohedral interesting? Rhombohedral stacking go as ABC, 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 right? If you take one unit cell from each layer and assemble big molecular through this multilayer, you're going to get essentially the Sush-Ripper-Heater model. And the consequence, is going to be all the orbitals located at this overlapping atoms, these blue atoms, they will repel each other through this very strong hundreds of millieV interlayer hopping, and they will not, be responsible for the low energy band structure. Well, what really matters for low energy bands around Fermi level is the electron coming from this A1 and the B, sort of dangling bonds at the end, and they will remain degenerate at 0 energy. They talk to each other very indirectly through hopping through all the N layers. As a result, you get energy dispersion that's proportional to momentum to the N's order, where N is a layer number, right? Just rather simple. If you got monomer graphene, this gives you the famous linear Dracon, huge Fermi velocity, nothing to do with flat band. But you can tune up the layer number N here, and very quickly, when you get to something like 4 or 5 layer, you got flat band for free, okay? If you compare the density states here with some parabolic band, you get an effective mass already on par with bare electron mass if you get to something like 5 layer. So that's really heavy mass. Something should happen, right? Let me remind you, there's no twist, there's no moraine. It's just part of the crystal, and you have a pair of eyes to look at them and isolate it. You get flat band for free, and there's another advantage of this rhombohedral structure is, because these two orbitals are located at different Z positions, you can easily break their symmetry and generate a band gap by applying a vertical electric field, which you can do with a gate, okay? And the consequence of that is, of course, now we have a semiconductor, right? And the size of the band gap in the semiconductor is solely dependent on how big electric field you apply. Well, what really matters for us is that when you open up the band gap, you're further squeezing the bottom of the conduction band. You make it more flat and enhance the density states even more compared to what I call pristine flat band that's degenerate at 0 energy without gating, okay? So there is highly tunable flat band in this very high quality material. Something hopefully should happen in the correlation spirit. At the same time, this is also a good place to look for barrier curvature and possible topological effect. Well, in graphene, there are 2 values, K prime value. They are time reversal pair, of each other. And you get big barrier curvature distributed at the band edge. Okay, you open up the band gap a little bit, you get opposite barrier curvature for connection valence band. And if you look at the 2 values, because they are time reversal pairs of each other, the same state in the 2 value will have to carry opposite barrier curvature, so the total integration is 0, right? Graphene doesn't break time reversal symmetry unless something happens spontaneously when you have flat band effect, right? That's our hope. When you combine the flat band, hopefully the exchange interaction between the 2 values can break the time reversal symmetry spontaneously, something that you used to use a high magnetic field to do. And then you can possibly have anomalous Hall or even quantized anomalous Hall effect. Okay, so this is the theoretical background. This is the device we're building experiment, right? So this is a rhombohedral 5-layer graphene in the middle, shaped into a Hall bar. So we can measure the longitudinal and transverse resistance at the same time. And as I promised, we're going to make use of a piece of top gate made of graphite and a piece of bottom gate here to tune two quantity that really matters. One is the charge density N, and the other is the displacement field D, which is a vertical field we can open up the band gap with. Okay? And experimentally, what we can do is simply measuring resistance, longitudinal transverse resistance as a function of charge density and vertical electric field, or how, controlling how big the band gap is. And we get a map like this at hundreds of millikelvin. Well, this is obviously more complicated than what you expect from just a band gap tunable semiconductor, right? There are all kinds of shapes that, this one I call as a bubble, this is a ring, there's some contrast between two domains with some boundaries. It's all kind of feature there that you wouldn't get by simply doping charges into a band gap tunable semiconductor. And I can tell you all of these are due to the flat bands that either exist at zero gating or generated by the electric field. Okay, I'm not going to talk about these, but let me dive into two experiments. The first one is related to the FCI Liang was telling you about, right? So he has already told you about, it reminds you of the fractional quantum Hall effect, which requires very high magnetic field, low temperature, very high mobility gallium arsenide materials. And of course, it's nice to have that at high magnetic field. You get fractional charge, fractional statistic, composite fermion things. But as an experimentalist, I wonder if you can do it at zero magnetic field. Okay, of course, theory also wonder about that. And that's the first thing that we found. Fractional quantum anomalous Hall effect. Anomalous means happening at zero magnetic field. So the setting is like we have a 5-layer rhombohedral graphene like this, and we control the twist angle between the top HB and the top layer of graphene to be close to 0 degree. Okay, that 0.7 degree is unintentional. We think it doesn't matter if it's 0 or 0.7 because there is a lattice mismatch to give you more rate already. And you apply displacement field, and turns out you can push these electrons to the flat bottom of the conduction band, and physically they will reside at this layer, which is opposite from where the moire is, right? But anyway, there is a moire in the system. And the consequence is that if you measure the Hall resistance as a function of the charge density or the fitting factor of the moire superlattice, you're going to get a series of plateaus. Some of them is quantized at integer times of h over e squared. So this is the integer quantum anomalous Hall effect. At the same time, there are, like, at that time, 6 fractional plateaus that's precisely quantized at h over e squared divided by some fractional numbers. Okay, this is a 2/3, 3/5, 4/7. 3 of them above half filling, the other 3 below half filling. Okay, phenomenologically, fractional quantum anomalous Hall effect. This is from last year, from year 2023. And as you notice, the RXX residue there is not so small, right? It's actually crazily big compared to the best fractional quantum Hall data. However, simply within 1 year, we're able to get a sample that shows much lower residue resistance at those dips. The smallest we can get now is probably something around 500 ohm if you look at the dip of 3/5 here. And that's because we're able to cool down to lower electronic temperature, thanks to the effort of Zhongguang making nice filters. At the same time, because now we're at a lower temperature, we can also review a couple more fractional states, like 5/11 and 5/9. So we have a total of 8 fractions at 0 magnetic field in this Rhombohedral Graphene HBM or superlattice. Okay, and the quantization is pretty good. 0.1% within the value, and that's really limited by just the noise level of our experiment. And this is not a single example. 5 is somewhat magic, but not that magic, because you can also get such kind of fractional Schrödinger or fractional quantum anomalous Hall effect in 4-layer or 6-layer graphene, as long as you twist it to be close to 0 degree. And and we have some other findings we call extended quantum anomalous Hall effect. And that is in the same sample, but phenomena happens at a really low temperature, and that will come up very soon in a couple of weeks. And we collaborate with reassurance group, where remind you, this is fractional quantum monoxide effect happens when the charges are residing at the opposite layer of the moire, right? Which is kind of bizarre. How do they even know there's moire, and why would they adapt themselves to the moire potential to give you this fractional state? But anyway, when you push these electrons to the layer of graphene that is right next to the moire, you actually also have FCI. It's not quantized at the zero magnetic field, but you can easily see them at something like 0.2 Tesla, which is very small. Okay, so this is a system that hosts a family of fractional Schur insulator or fractional quantum anomalous Hall effect at both the moire proximal side and the moire distant side. And phenomenologically, they are very different. So it's a very rich system to study. However, here's the issue. Okay, so this effect in this material is not predicted by any theorist, right? Part of the reason is because these electrons are residing at the opposite layer of moire. So nobody would expect that moire will have a dramatic effect on the property, but it does. So after the experiment, we have seen an explosion of theoretical works trying to explain what's going on here. However, there's no consensus yet. And this system is totally different from twisted MOT2 in almost every sense. MOT2 has very strong spin order coupling, and as Liang told you, this spin, a skyrmion lattice and the emergent magnetic field. Well, this system has nothing. Carbon has very weak spin order coupling. Carbon doesn't have this layer layer pseudo spin thing. Doesn't have the skyrmion in real space. Nothing like that. However, it gives you the same phenomena of fractional quantum anomalous Hall effect. So this has been, still at a very active frontier of FCI research, and we hope to contribute more and help theorists to figure out eventually what's going on. Anyway, so this is what happens when you have the moire superlattice. And next, what I want to show you when we get rid of the moire superlattice, right? I mean, what I mean by getting rid of the moire superlattice is by increasing the twist angle so that the moire superlattice become very small in real space, and they have negligible effect on the low energy band structure of physics. So what we find in this case is superconductor. And it's just not superconductor. It's something that's very different from other superconductors in the sense that you can think of it as a magnetic superconductor. Okay, let me explain to you what I mean by that. So this time, we don't need moire. Okay, large twist angle between graphene and HBN, and I'm using an example of tetralayer graphene. But pentalayer, 5 layers should show a similar phenomenon. Anyway, it's the same trick, right? You make a Hall device, you vary the charge density, you vary the gate displacement field, and you're looking at one quadrant of this phase diagram that corresponds to when you open up the band gap and dope electrons to the bottom of this very flat, bottom of the conduction band, okay, where the correlation effect is supposed to completely dominate. And you find in the phase diagram, there are 4 regions that shows vanishing resistance, SC1, 2, 3, 4, okay, 4 regions. And the TC of these superconductors are not high at all. These are at most like 300 millikelvin. You can just look at the temperature dependence here. However, there's something already weird that you can notice, okay? SC1 and the SC2 seems to have a lot of fluctuations there. Well, that doesn't really happen to SC3 and SC4, okay? And turns out SC3 and SC4 are just normal in every sense you can tell, like applying a small outer plane magnetic field, you easily kill this very weak superconductor on the order of like 100 millikelvin. However, SC1 and SC2 seems to be very different from SC3 and SC4, okay? Not only there's fluctuation in SC1, SC2, there's also a lot of fluctuations in the neighboring metallic states. Okay, I'll tell you what that means later, but for now, let's look closer to this SC1. You may think, okay, you are scanning the gate voltage, right? Which is an external perturbation to the material. Maybe that triggers something in the system, so your sample is not in an equilibrium or stable state, and that is why it's fluctuating. However, you actually can also get that kind of flickering by parking the gate voltage at a specific value without changing them at all. You just go into some state inside SE1 without tuning any gate voltage, just watch it as a function of time. The only excitation you give to the system is the AC current that you have to use to read the resistance. It's also showing this kind of temporal fluctuations. Most of the time it's superconducting, it's zero resistance, but from time to time you get a spike and then it goes back to zero. In addition to this temporal fluctuation, the same state, if you apply outer plane magnetic field and switch it back and sweep it back and forth, you're going to get hysteresis. So what I mean by hysteresis in a superconducting state is, both before and after some switching happens, you get zero resistance. Okay. However, there is a moment when you sweep magnetic field that, very briefly, it deviates from zero and give you a finite resistance. And that gives you the spike in resistance. Okay, and when you go back and forth in magnetic field, there are two spikes that do not overlap with each other. So there is a hysteretic behavior in response to magnetic field, which just feels like a magnet, right? A magnet will give you this kind of hysteresis, and a magnet could, fluctuate spontaneously by itself if the temperature is not low enough, and that. Basically, phenomenologically, the superconductor feels like a magnet. Yes.
Trying to understand how a superconductor can get finite resistance even in switching the polarity.
Yes.
You have to somehow, block the supercurrent path. Right?
Exactly. So what we think may be going on is that when the switches, there has to be a domain wall moved in, and if that domain wall is trespassing the path from source to drain, the domain wall could be resistive. Especially in this case, if these two superconducting states correspond to opposite value polarization, then this tunneling across the domain wall has to violate the momentum conservation, and that has to be resistive.
But wouldn't it be easier for the superconducting regions to find a circulation path to this?
Yeah. So basically, I think what you can see here is when this path, the domain wall really cuts through the path completely, right? There may be cases where the domain wall is in parallel with the current, and your supercurrent still shorts everything, and you wouldn't even see a resistance fluctuation or deviation from zero in that case. Of course, this is my guess. We're not doing any imaging,
But do you have samples that just show zero resistance as a function of magnetic field, no switching?
It does. So basically, as you can see here, the coercive field of this particular case is very tiny, right? Like 20 millitesla. We do have sample that shows bigger coercive fields, like several times bigger. And in those cases, the fluctuation happens much less frequently.
No, but with the switching, do you still see finite resistance?
There is, if you are patient enough, there could be a switching, but it's much less frequent than here. So exactly how fast does it switch, and how does it depend on temperature, and variation from device to device is a lot of details, because domain wall thinning by some defect there could vary from case to case a lot. But our general observation is when the coercive field is small, the fluctuation is very frequent. When the coercive field is big, it's much less frequent at the same temperature. Okay. So it feels like a magnet, right? So I'm telling you, usually superconductors do not like magnetic field, right? They try to expel magnetic field out if you're in the bulk. Of course, in 2D, magnetic field can always penetrate through. And so superconductor in 2D may be getting along with magnetic field, but what I'm telling you is some superconductor not only getting along with magnetic field, but they themselves behave as magnet, right? That's the weird thing. To show you another map, right? This is taken at the 0.1 Tesla magnetic field. This is beyond the coercive magnetic field of the hysteresis. So what happens in this case is that you measure resistance again as a function of N and D. Suddenly, all those fluctuations are gone, okay? Because you are beyond the coercive field, 0.1 Tesla is able to completely stabilize one of the superconducting states. So that's why it's not fluctuating. Not only stopping the fluctuation in the superconducting state, but also stopping the fluctuation in this very big neighboring metallic region where you had a lot of fluctuation here, but 0.1 Tesla is able to completely heal them. Okay. So how much time do I have? Yeah.
5 minutes.
5 minutes. Okay. Let me make it quicker. So basically, we can do further analysis by applying magnetic field and measure quantum oscillation in the metallic part. And we can measure the anomalous Hall resistance by anti-symmetrizing data at 0.1 and minus 0.1 Tesla. And you see there's a lot of anomalous Hall signal here that indicates time reversal symmetry broken spontaneously. Okay. Combining, and there's magnetic hysteresis in this metallic region. So combining this analysis, we think what's going on here is that, okay, in graphene, you have two internal degree of freedom. One is called spin, the other is called value. So every band structure will have 4 copies corresponding to the combination of spin and value. And if nothing interesting happens, the Fermi surface cuts through all the 4 copies equally. So time reversal symmetry is not broken. However, if the flat band effect is strong enough, the exchange exceeds the flatness of the band, you're going to possibly have a so-called quarter metal where you have a single flavor, where the Fermi level just cuts through one spin and the value polarized state. And that's what we think the parent state of this weird fluctuating superconductivity is. And this anomalous Hall signal, actually, if you warm up to above TC, inside the region where you used to see superconductivity, you actually still have this anomalous Hall resistance and the magnetic hysteresis. This is already different from all other superconductors. And this indicates the time reversal symmetry is broken at the orbital level. So, we think this is also related to BC-BCS crossover if you look at the coherence lengths. But anyway, let me summarize. So there's fluctuations and there's magnetic hysteresis in the superconducting state. That's a new observation. And there is anomalous Hall resistance at the B0 and magnetic hysteresis above TC. That's also a new observation compared to all other superconductors. And this implies that it's a spin and value polarized superconductor, which has to be finite momentum pairing, which falls into the category of chiral superconductor because time reversal symmetry is broken at the orbital level, not by spin. Okay, and we don't know if this is topological or have Majorana yet. We don't know what is the mechanism. However, I want to remind you this is simple carbon. Okay, and this is crystal. There's no twist. It's as simple as it could be, chemically and structurally. So I want to end with highlights of how rich simple crystalline carbon could be. Okay, this is a phase diagram of Rhombohedral graphene with Moray. We have FCI here. We have the integer Chern here. We have layer antiferromagnet. This is the horizontal axis is density. Vertical axis is the displacement field. Okay, we have CW. We have all kinds of interesting states. And even in the absence of Moray, the phase diagram is also incredibly rich. Multi-Freud here, you have half metal, quarter metal, Wigner crystal, we suspect, and the superconductor. And when you approximatize by TMD, you get some more changes. So this is a good example to show you, we're talking about quantum materials, but we don't even understand how the simplest carbon in the crystal form works. And experimentally, we have shown it's very rich. So this is, where I think I can connect to the theme of this workshop. Maybe machine learning can help us understand this, right? And go beyond there. Thank you for your attention.
Thank you for exciting results. Any further questions?
Are you able to look at a finite size dependence of these tunneling things? It reminds me a little bit of sort of molecular magnets when you say, you sweep a domain more through the system. So it's a very non-equilibrium process, which presumably has some nucleation properties.
Okay, that's a very good point. We haven't done it. Right now, the size of the sample is limited by 2 things. It cannot be too small because you need to put at least 4 electrodes to measure it. It cannot be too big because rhombohedral has a tendency of relaxing to burn out, right? So the bigger it is, the more likely it is to generate some speed of burnout. So we tend to keep it the size of the device to be on the order of 10 microns, which is just enough to put in 4 or 5 electrodes. I think that will be the next thing that we can explore by either going to smaller size or bigger size and see how the microscopic works. But I think another approach would be instead of using this global transport approach, you use some scanning probe things that can visualize things at microscopic scale. That may be more direct to see domain walls and things.
How these symmetry broken superconducting states compare to earlier reported ferromagnetic superconductor?
Very good question. Ferromagnetic superconductor is mostly about the spin got polarized, right? Ferromagnetic superconductor does not show anomalous Hall resistance above TC. For some reason, I don't understand.
Okay.
Phenomenologically, this is the first time that the superconductor shows anomalous Hall resistance and the hysteresis above TC. We think it's not only ferromagnetic, but it is ferro-orbital magnetic. So the tangential symmetry is broken at the orbital level.
Okay, great.
Yeah, in ferromagnetic superconductors, I mean, it should be also orbital sort of
Exactly.
Originated because they're uranium-based, right? And in uranium magnet is mainly orbital, right?
Yeah, but I don't understand why they didn't observe anomalous Hall for TC.
Maybe they should try.
Okay, let's not, yeah.
Thank you.